This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Welcome back to the WE Heraeus International Winter School and Gravity and Light. Today with our 9th problem sheet on metric manifolds. As always, we start with the short true or false section. Let's begin. The Levi-Civita connection is torsion-free. That's true, since we just look at torsion-free connections. The Levi-Civita connection is called metric compatible since it satisfies this equation. This is not true since for the compatibility condition means instead of the G here a 0, the 0 vector. The Levi-Civita connection is the unique affine connection that can be constructed from the data of a metric manifold. This statement is true, and we will see this in exercise 3 of this problem sheet. The Levi-Civita connection gives rise to connection coefficient functions with gamma RA symmetry bracket BC equals to 0 in any chart. This is not true, since this part of the connection coefficients are not of tensorial character, so maybe they vanish in one chart, but surely not in any. The Levi-Civita connection arises by requiring that the autoparallels are the curves of stationary length. That's quite true, and we also will see that, or we already saw that in the lectures. So in this question, only answer 1, 3 and 5 are correct. Number B. Which statements about metrics on a d-dimensional smooth manifold are correct? The first question is, a metric with signature dd is called a Riemannian metric. This is not true, since a Riemannian metric has the signature d0 or 0d. A Lorentzian metric has signature 1, d minus 1. That's quite true, or it could also be d minus 1, 1. On a Lorentzian manifold, vectors x of TPM are called G-null vectors if G of x, x equals to 0. That's exactly the definition of G-null vectors, therefore the statement is right. A metric provides an inner product on each tangent space TPM. That is not correct, since for an inner product we need the positive definiteness. And this is not given for any kind of signature. It's true for a Riemannian metric, but it's not true for any other. An inverse metric fed with a covector yields a real number. That's not true, since an inverse metric eats two covectors, and if you just fed one in, you have one slot left with where you can fed in a covector, so it's a 1-0 tensor field. Which statements about geodesics and the length of a curve are correct? A Riemannian metric gives rise to a well-defined notion of length of a curve. That's true. The length of a curve is obviously not invariant under a reparametrization of this curve. This statement is not true, since here is written a not. Under some circumstances, the curve length is invariant under reparametrization. We will see this later on. So this statement is incorrect. A geodesic is a curve of minimal length. That's not true. A geodesic is a curve of stationary length. The condition for a curve to be of stationary length is that it be a solution of the Euler-Lagrange equations for the Lagrangian L of x equals to square root of g of x, x. That's quite true. We already see this in the lectures. A geodesic on a metric manifold satisfies the autoparallel equation. Therefore, some words have to be said. Geodesics describes the shortest curves between 2 points. And the autoparallel describes the straightest curves between 2 points. So these two notions are in general disjoint. But we can see that if we choose the Levi-Civita connection, these two notions are the same. We continue with exercise 2, recognizing and dealing with different signatures. First, there's a statement written. Other than 1,1 tensors, 0,2 tensors do not have eigenvalues but signature. And signature is the topic of this exercise. Let G be a symmetric 0,2 tensor over some vector space. Question. You are given the following 4 sets of G null vectors in the vector space. The surface of a double cone centered in the origin, a point in the origin, a straight line through the origin, and a plane through the origin of the vector space. We are now asked to determine the possible signatures of the respective G in each of the 4 cases. So, since we are in a vector space, I firstly will introduce a coordinate system. I call the axes x1, x2, and x3. Now we have to think about what is the equation for the cone surface. The equation for the cone surface is x1 squared plus x2 squared plus x3 squared equal to 0. Minus x3 squared equal to 0. This can be fulfilled by G of x, comma x in the following signature sense. We first take plus, plus, minus, which yields exactly that. But it also could be that we take minus, minus, plus, which yields the same equation, but with different signs. Here a minus, here a minus, here a plus. But since this is 0, we can just multiply with minus 1 and get the same result. So this is the signature for case A. Case B. In case B, we just see that the G null vectors are the point in the origin. What does that mean? That does mean that we only want G of x equals to 0 for the null vector. But therefore, it should not be possible that we can add some squares of vectors up, some squares of components of vectors up to 0. Yeah, this is possible. This is not possible. If we just have plus, 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 then we never will end with a 0, or minus, 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 without taking the null vector. So this is the signature for this kind, for this kind. Number C. We see here that the straight line through the origin should be the set of all G null vectors. That would mean that we need the signature plus, plus, null, or minus, minus, null. Since we just want to plug in for this x3 everything we want, and it doesn't count, but the other 2 entries should not be able to add up to 0. This is exactly given by this signature. In case D, we see the plane. The argument is similar, but a little bit different to the case C. In this case, we just have, that is, let me think about the right correction, is 0, 0 plus, or 0, 0 minus. I repeat the argument once again. We should be able to plug in for x1 and x2 everything we like to, and it doesn't matter. But for x3, yeah, it never could add up to 0 because it's just one component. So, in the end, these are all the possible signatures. In the next question, we are asked, for each signature you found, indicate the set of vectors of positive length in the drawings. Therefore, we have to look at each signature. First, we look at the minus minus plus signature of the cone. I indicated by that, and all positive lengths are on the outside of the cone, as you can easily calculate. For this signature type, we see that all positive vectors lie in the cone. This is interesting for general relativity later on. For plus 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 or minus minus minus, only the plus 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 have some positive length. But then it's all around the point, without the point. For minus, 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 we just have negative length. In the plane, the same argument holds. For the plus, 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 not for the plane, I'm sorry, for the straight line, everything outside. For the plus, plus, 0 signature, and for the minus, minus signature, we don't have any positive length. And the same argument holds again for the plane, where we have everything outside. For the signature null, null, plus is of positive length, and for the signature of null, null, minus, there is no positive length. Okay, therefore exercise 2 is complete. We continue with exercise 3, Levi-Civita connection. For vanishing tensor torsion, the Levi-Civita connection is already uniquely determined by the requirement nabla of G equals to 0. Let's start. Suppose we have a torsion-free and metric compatible connection. That means vanishing rank 3 tensor fields. T is the torsion, which we set on 0, and nabla of G is equal to 0, where G is a 0, 2 tensor field, so it eats 2 vectors, but although the covariant derivative has here an open slot where you have to fed in a vector, in this sense, this object is a 0, 3 tensor field. Okay, first we are asked to recall what t equals 0 implies for the connection coefficient functions with respect to a chart. I first write down the definition of the component functions. T, A, B, C is equal to 1/2, not 1/2, gamma ABC minus gamma ACB equals 0. If this is the case, we see that all antisymmetric components are already 0. We also can write down gamma ABC equals to gamma ABC plus gamma ABC. But since this is the definition of the torsion, it only yields that. Good. That we will need later on. Question 2. Expand in terms of the connection coefficient functions. Here we are asked to do the covariant derivative of a 0 to tensor field G with respect to the basis vectors of the vector space. We just have to plug in the definition, which is del after del XA of GBC minus gamma A on the last slot. Here we need an open index. B G N C minus gamma N, take again the same summon, C A G B N. This is just the definition. For later on, I will now introduce a short notion. We define GBC, A as this guy, and I will use it from now on. Since we have that the covariant derivative of G is equal to 0, we already know that this equation yields 0. Okay. Expand the second. plug in the definition again. It's del after del xb, and I already introduced the short notion, so I will use it. It's g c a comma b minus gamma n b c g n a minus gamma n a b g c n. Now expand the last term. It's all the same. G a b comma c equals to gamma index, summation index n a c g n b minus gamma n c b g a n equals to 0. That's it. Question 3. By adding and or subtracting 1, 2 and 3 in a clever way, we obtain gamma ABC equals to 1/2 of G inverse AM from del of del XB GMC plus del after del XC GMB minus del after del XM GBZ. And conclude that the conditions nabla of G equals to 0 and T of T equals to 0 uniquely determine the connection coefficient functions in terms of the metric. Let's start. We add equation 1 to equation 2 and subtract from there equation 3. And we know all this is 0, then all these 3 equations are 0. Yeah. First, just plug in the definitions. It's G, B, C, comma, A minus gamma N, B, A, G, N, C minus gamma N, C, A, G, B, N plus G, C, A, comma, B minus gamma N, C, B, G, N, A minus gamma N, A, B, G, C, N minus the last equation G, A, B, comma, C plus gamma N, A, C, G, N, B minus plus gamma N, B, C, G, A, N equals to 0. Now, first look whether there some gamma symbols vanish. Okay, we have to look carefully. We look for gamma NBA. NBA are again here, it's AB, but from the first, from the first question, we already know that gamma NBA is equals to gamma NAB. Therefore, we just can switch these 2 slots. And we also know that the metric is symmetric, so we can change N to C, the places, no, the right one. And we can also change this 2, and we see that they 2 add up to -2. So this we will just keep in mind. We look for the next coefficients. We see gamma NCA GBN, where we found this again. Here gamma NAC GNB. We can also exchange here the NB and the to BN and the AC to CA. We see this is 2 times the same term, but with different sign, so they cancel each other. Next term, we look at gamma N CB GNA, and we also found it here. Gamma N BC can be switched. GAN. Nice. Same argument as before. So we see this is given twice, and only these 3 other components are still there. So this is equal to -2 gamma N A B G C N plus GBC, comma A plus GCA, comma B minus GAB, comma C. So, yeah, in order to get to this equation, we have to bring this on the other side and multiply with the inverse metric. So, make plus 2 gamma NAB GCN and multiply both sides with G inverse CM. Now, here we find gamma N A B GCN, I forgot the 2, G inverse CM equals to G inverse CM times GBC, comma A plus GCA, comma B minus GAB, comma C. Okay, we can use here the delta criteria that GCN times G inverse CM is delta NM. Therefore, we can just rename this index n to m. And we also will divide with respect to 2. Therefore, we see gamma MAB is equal to 1/2 G inverse of CM GBC, comma A plus GCA, comma B minus GAB, comma C. In this equation, we just have now to find, we just have to rename all indices in the right manner. Since only the C index is contracted, we only can rename this as a dummy index on the one hand side, but if we want to rename one of the other index, we have to do it on both sides of the equation. So, first of all, we call MA, M goes to A, but therefore we first have to call A another way. We call A to B, but therefore we have to call B to C, but therefore we have to call the dummy index C to M. This is what it has to be done. Let's do that. That is equal to gamma, okay, I said M goes to A, I say A goes to B, I say B goes to C, is equal to 1/2 G inverse of C goes to M, M goes to A, yeah, that's right, G of B goes to C, C goes to M, A goes to B, plus C goes G of M, A goes to B, B goes to C, minus G of A goes to B, B goes to C, C goes to M. So, and if we look it up, these are exactly the expression which are written above. Therefore, this problem is finished, and we see that from the condition that we have a torsion-free affine connection, and we also have the compatibility criteria that the covariant derivative of G with respect to any vector field is 0 yields directly to the connection coefficients of the Levi-Civita connection. We continue with exercise 4 on metric manifolds, massaging the length functional. Modifications of the length functional that simplify calculations but do not change results. Question 1. Let gamma be a smooth curve from 0, 1 to m on a smooth manifold MOA. Now consider a second curve, gamma tilde, going from 0 to 1, going from 0, 1 to m, defined by gamma tilde of lambda defined with respect to gamma of sigma of lambda, where sigma is a map from 0, 1 to 0, 1, which is increasing and bijective and smooth. We should now show that the length of both curves is the same. Therefore, we start with the left-hand side and calculate to the right-hand side. Plug in the definition first. L of gamma tilde is equal to the integral from the limits 0 to 1 d lambda square root of g a b evaluated at the point gamma tilde of lambda times gamma tilde dot with respect to the eighth component of lambda times gamma tilde dot b. Square root close, bracket close, lambda missing. So, now plug in the definition of gamma tilde and plug in the definition, I will remind you on that gamma tilde dot, the eighth component, is just defined as x after gamma tilde, the eighth component, prime, evaluated at lambda. This is just the definition of the component functions of a vector. So, integral from 1 to 0, from 0 to 1, d lambda, and I here missed the lambda again, is equal to the square root of GAB of gamma of sigma of lambda bracket 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 times x of gamma tilde, but I know that gamma tilde is just gamma after sigma, so gamma after sigma, the eighth component derivative evaluated at lambda times the same guy again, bth component derivative evaluated at lambda. Square root finished. So, in the next step, we first will use here the chain rule. It's again the integral from 0 to 1 d lambda square root of GAB of gamma of sigma of lambda bracket 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 times chain rule, autoderivative, x after gamma, eighth component prime evaluated at sigma lambda times sigma dot lambda in a derivative times x after gamma bth component derived, the derivative taken, evaluated at sigma of lambda times inner derivative sigma dot lambda. Square root close. Now we see that this is 2 times in here, so we'll shift it out of the square root, and the square occurs with the square root, and we see that the gamma depends on the g depends on gamma after sigma, and all of these terms as well. So one more step is needed here. We see that we have to change our parameter. We do a substitution, so-called. We say we introduce a gamma hat, which is defined by sigma of lambda, but to transform this guy correctly, we need to calculate d of lambda hat with respect to lambda, which is equal to sigma dot lambda. Aha! As I mentioned, we plug this guy, we bring this guy in front of here, and if we write this equation somehow like that, we see that we already have changed this guy. And now we also plug in for all sigma of lambda, just lambda hat, this guy, and this guy. Yeah, I will write it down and let, in the first place, the limits open and explain what I do there in a second. It's the square root of GAB of lambda hat. Sorry, it's truly not right because we have to evaluate at a point in the manifold. It's gamma of lambda hat times x after gamma, 8th component, prime, lambda hat times x of gamma, bth component, derived, taking the derivative, lambda hat. Okay. I already say that I do not talk about the limits yet, but since we know that the lambda function is increasing bijective, we know that the limits stay the same. So now, last step, we already know that these are just a longer notation of gamma, 8th component, derived of lambda hat. This the same for beta. For here, exactly the same is written as here, just with lambda hats instead of lambdas and with gammas instead of gamma tildes. Therefore, what is written here is L of gamma. Therefore, we have shown that the length is invariant under increasing bijective reparametrization. Question 2. Show that the Euler-Lagrange equations for Lagrangian T have precisely the same solutions as the Euler-Lagrange equations for the Lagrangian L, which is defined as the square root of T. If, of the latter, one only selects those solutions that satisfy the condition T equals to 1 on their parametrization. Okay? We will just calculate this. I think you all know how the Euler-Lagrange equations look like. It's defined as dl after dq dot 8th component. After you've taken this, you take the derivative with respect to the parametrization minus, with respect to the parameter, minus d of L after dqa equals to 0. Okay, now just plug in the definition of square root of T for L. This is equal to d of square root of T dq dot a dot minus d square root of T dqa equals to 0. Aha. We now have to do two things. We can first apply here the chain rule in both parts. That means we just do the derivative of del of square root of T, and you all know how this works out. It's just 1 over 2 of the square root of T of d of T dq dot a dot minus, the same guy appears here, 1 over 2 of square root of T dt with respect to dqa. And since we know that T should be 1 all along the parametrization, we can pull it out here because we just take the derivative with respect to the parameter. Aha. So what is written here again? It's 1 over 2 of square root of T dt dq dot a dot minus 1 over 2 square root of T dt dqa equals to 0. Yeah, just cancel this two guys, and what is written there is again the Euler-Lagrange equations for T. You can ask, why the hell should we do that? It's very simple. Because we see that in the length function we have a square root here, and we now show that the Euler-Lagrange equations do not change whether we have a square root or not. That simplifies calculations. We continue with exercise 5, a practical way to quickly determine Christoffel symbols. In a concrete case, rederiving the Euler-Lagrange equations is quicker than using the general formula we found for the Christoffel symbols in exercise 3 of this exercise sheet. Question. Derive the geodesic equation for the two-dimensional round sphere of radius r whose metric in some chart is given by this expression. Let us shortly remember what the geodesic equation is. It was gamma dot dot eighth component plus big gamma a b c gamma dot b gamma dot c equals to 0. I already write here the gammas, and these are the gammas of the Levi-Civita connections, since we decided that the geodesic should also be the autoparallels. Okay, we keep reading. And the metric is given by this expression, and we should derive all this via a convenient Euler-Lagrange equation. And we lighten the notation with these two guys. Aha, what was all this about? We just should write down the Euler-Lagrange equations. We had it with respect to the length function L. It has this form. I should use the same L as before. And I should keep my notation straight, so I should use again the gammas, gamma dot A and gamma A. I have to explain some things. We can now, instead of using the length function, although the square root, where was a square root in there, although the length function without the square root, what we derived in the exercise before. So L in our case is just G A B gamma dot A gamma dot B. Now I say once again what gamma A is, and gamma A is just defined, gamma A of lambda is just defined as x A after gamma of lambda. So in our case it's just theta of lambda and phi of lambda for A is 1 and A is 2. Good. Now write down the explicit form of the L in our case. L equals to GAB, these guys, so we see that it just appears if the two indices are the same, because it's diagonal, it's r squared times theta dot squared plus r squared times theta, sine square of theta times phi dot square. This is the guy we have to calculate the Euler-Lagrange equations for. Now we do that. We first do the derivative with respect to the first entry. And the first entry was theta. Theta dot minus dl after d theta. Deriving this guy, we see in the first part gives 2 times r squared times theta dot. The second term gives nothing in here, and here we see we have to derive this guy. It's 2 times r squared times sine of theta times cosine of theta times phi dot squared. I forgot here the dot. Here it is. So I have to take the derivative here again. So this is all equal to 0. So see, it's 2 times r squared times theta double dot minus 2r squared sine theta cosine theta phi dot square. Now I can divide through 2 and r squared, and I have the first Euler-Lagrange equation. And I will write it down. It's theta dot dot minus 2 times r squared. I should remember what I divide through. Sine of theta cosine of theta phi dot square equal to 0. Now do the same thing for this second equation. It's dl after d phi dot minus dl d phi. Good. Let's calculate that. This guy again, we see that only the second term contributes here. That's r 2 times r squared sine squared of theta times phi dot square phi dot, do the derivative, did the derivative, dot, minus second term doesn't appear anywhere. So we do here the derivative with respect to the parameter, and we see now theta and phi depends on this. So we have to derive both. We need the product rule. It's 2 times r squared, bracket. Here for the autoderivative, 2 times sine of theta times cosine of theta times theta dot times phi dot plus the other term sine squared of theta times phi dot dot. I also can divide this with respect to 2r squared and bring it in the same form as this equation. Therefore, we have phi double dot plus, yes, 2 times, the 2 is still there, sine through sine squared is 1 over sine, cosine through sine is cotangent of theta times theta dot times phi dot equals to 0. Since I already said, yeah, and I always divide through, not by. Okay, just joking. Since I already said that I want that the geodesics should also be the straightest curves, we now can read off the gamma symbols of the Levi-Civita connection right from these two equations. I will write down the autoparallel equation, what I always use in the same sense as the straightest curve. It's just a notion. I write it down again to read up more easily. Gamma dot B, gamma dot C equals to 0. Therefore, I can see from the first equation that gamma 1, it's the A over here, BC, we can look what BC is. It's 2, 2, since only phi dot appears and this multiplied. We have that this is minus sine of theta cosine of theta. That is the first Christoffel symbol in this chart. Now we just look at the second equation, and we see that from there we can read off gamma 2, then here's a 2, of 1, 2, very good, is equal to 2 times cotangent of theta. And I now really did a small mistake, since we know that gamma, from the torsion free, we know that gamma ABC is gamma ACB, we have to distribute the 2 over the 2 gamma symbols, gamma 2, 1, 2 and gamma 2, 2, 1. Therefore, I already answered the next question. Yeah, we finished to calculate the Christoffel symbols for the round sphere. Continue with exercise 3 on metric manifolds. 6. Properties of the Riemann-Christoffel tensor. Various algebraic symmetries that a plane Riemann curvature does not feature. Question. Show that the chart-induced basis fields act on the coefficient functions as the following. In order to show that, we start with the following expression. G inverse of AB times GBC. Yeah, and we will calculate that. We will see that this is the same as del AC. Now we can do the derivative with respect to this guys on both sides. So to dx del after del xt, and here also del after del xt. Since we know that the delta function is constant, we know the left-hand side is 0. It's not the delta function, since we know that this guy is a constant with respect to the vector field. Okay. On the right-hand side, we need the product rule. Therefore, we do del after del xt G inverse of AB times GBC plus G inverse of AB del after del XD of GBC. We are almost there. We just bring this guy on the other side, or this guy better, and multiply with the inverse of GBZ. The inverse of GBZ, since we already use B, we call it GCE, for example. Yes. And from now on, if I have the G with index up, it's always G inverse. It's just a short notation, and I will surely forget it anyway. So let's do that. Calculate this. Then we have del after del XD GAB times GBC GCE equals to minus GAB GCD. No, not GCD, GCE. Del after del XD GBC. So we see here again a delta. So this is delta BE. So we just can rename B to E. With my Magix pen, it's very easy to do that. Yes, and if we compare the indices, we see that these two guys are the same. The second question is, use normal coordinates to find an expression for the Riemann-Christoffel tensor, which is given by RABZD, is defined by GAK-RKBZD at a given point P in terms of the metric GAB and its first and second derivatives at that very point. What does normal coordinates mean? It's a very good notion because in normal coordinates there exists a point for which the gamma symbols vanish. And this we will use heavily in this exercise. So, before I start calculating, I will define one more notion just for shorthand side. It's if you do the second derivative of GAB XC dxd, then I will denote that by GAB, CD. This I will use heavily. Okay, let's start. R, A, B, C, D is equal to G, A, K, R, K, B, C, D. Plug in the definition of the Riemann curvature. That was given by 1/2. That was given by, I'm confused, I'm sorry, del after del xc of gamma ABD minus del after del xd of gamma ABC plus gamma gamma minus gamma gamma with the indices distributed in the right way. But as I already explained, we are in normal coordinates, so the gammas are 0. Therefore, I can cross them out. What I also can obtain here is that these two expressions are symmetric, or are the same, just with C and D exchanged. This I will denote by minus C, D. Now, in the next step, I just plug in the Riemann-Christoffel symbols, which were defined by 1/2. The GAK stays in front from here, D after DXC, big bracket, of, now the definition, it was something like GKM of del after del x b GMD, what I shortly write down by GMD, B plus GBM, D minus GBD, M. Bracket close, and the same term with minus C and D exchanged. Okay. What I need to do now is to apply the chain rule, the product rule at these two guys. That's 1/2 GAK of, I denote the derivative shorthanded, GKMC times GMDB plus GBMD minus GBDM, first part of the product rule, plus GKM times GMD, BC plus GBM, DC minus GBD, MC. And all the same stuff with C and D exchanged. In the next step, I will use this expression, which we calculate in the first question. So plug in this definition. It's GAK times minus, I bring it out, need a little bit more of space, minus G, I have to see, it is K, I need new indices, L, because it's a summand, times G, M, I need a new symbol, call it N, of D after dx, what is written above, it's G, C, and in the G, the two indices are summed over, Ln. I think I have done it right, so I can go further on. Let me see, short second, yes, that's right. I write out the other terms as well, plus GBMD minus GBDM plus GKM GMD, comma BC plus GBM, comma DC minus GBD, comma MC, close bracket, minus CD exchanged. Now I can use again the delta here. GAK, GKL is delta AL, which means that I can just call the L in here A. This symbol still stands in front. It's minus 1/2 GKL GANC of all this bracket terms, blah blah blah, minus CD. I just do not like to write it again. So now see whether we can see there somewhere the Christoffel symbols again. And yeah, it's possible. Actually, as one can obtain, let me think about, yes, exactly, this was the definition of the Christoffel symbols. That is, this guy, GKL, takes the role of GKM, GKL, and all these guys in here, is it right? Yes, it is, are together, I forgot a bracket here, see, are together the Christoffel symbol again. So, since I know this is already 0, the whole term vanishes. Only this term overlives. And in here, the same happens with CD exchange. So the first term of this both terms in CD exchange vanish as well. And just these 3 guys overlive this. Okay, I write it down again. It's minus 1/2 GAK times G. Did the indices wrong? GAK times GKM GMDBC plus GBM DC minus GBDMC. That's right. And now I take the minus CD part, means 1/2 GAK times minus minus gives a plus, GAK GMC BD plus GBMCD. I need a bracket here, otherwise the signs are wrong. Here, a comma, minus GBC, MD. Now I really write out also the CD combinations. What I see here, and I forgot the GAK, I forgot the GKM term over here again, I'm sorry. I easily do here bracket and delete this guy. So now it's right. And here has to be a minus sign as well. Okay. Now I look closely and I see that this term vanish with this term, and only this, and this term overlive. And I have here also again a delta AM, so I call all M's A. It's minus 1/2 GADBC minus GBDAC minus GACBD plus GBCAD. And this is the result we like to arrive. And I forgot a bracket over here. And I think I've done a small mistake in the fourth line, and it was this one. I pulled out the minus sign. Here is a plus sign. Plus, it's okay. I have a minus sign in front of all. It's still okay. Here I made the mistake. I pulled out a minus sign over here. Sorry, I'm really sorry for confusing you for the sign mistake. Here has to be written a minus, since I plugged in the definition of this guy, what I have calculated above. The minus is coming in here. Then I pull it out, but then I get another minus over here. Okay, this goes through. See, here is a plus. Then all minus are wrong. So how can I do it in the best way? Fix it. I think I kill this minus and this minus, and yep, now the job is done correctly. Yeah, sorry for confusing you. But as you see, this is just in calculation with indices. You need to get used to, but it's not difficult, it's just a matter of concentration. Therefore, this question is answered, and we go on to the next. We continue with the last exercise, and we are now able to show in normal coordinates that RABCD is equals to minus RBACD. So, we now show some Riemann-Christoffel tensor properties. Okay, we start. Definition, or what we calculate, was that RABCD is 1/2 of GADBC minus GBDAC minus GACBD plus GBCAD. What we are looking for is that if we exchange all ABs down here to BA, we want to find this index combination just with a minus sign. I write it below. So we want to BD, AC. Here we want to have a D, BC, and here we need a BC, AD, and in the last term we need a ACBD. Yeah, let's look it up. ACBD, here with a minus sign. Perfect. BCAD, here, minus, minus, plus. Perfect. ADBC, we found over here. BDAC, we found over here. So, this is minus RBACD. Very simple, actually. Go to the next question. We now show that RABCD is equal to RCDAB. We write out again what you calculate two questions before. It's 1/2 GADBC minus GBDAC minus GACBD plus GBCAD. What we are looking for now is if we exchange AB to CD. Okay, write it down. Every A is getting a C, every D is getting a B, every B is getting a C, every C is getting an A. No, I've done a mistake. And yeah, because B is going to D, I'm sorry. Same again, B goes to D, D goes... I'm sorry. I just want to write down the index combination. D, B, C, A. And here's C, A, D, B. And here it is D, A, C, B. Aha. Do we found this index combination again here? It's in this round we have to do one more step. And this is, we know that the G is symmetric. That means AD is the same as DA. And what we also know is, since we derive 2 times in the same coordinate system, the Schwarz rule holds. So I write it down. I just rewrite G, D, A, comma, C, B. Ah, it's this guy we are looking for, with the right sign. Minus, here again, just the Schwarz rule, G, D, B, comma, C, A, times, here again, just the Schwarz rule, and the symmetry of the metric, C, A, D, B, plus, and the last term, I forgot about this guy here, which goes with this guy, and the same sign, plus, I write it down here, G, C, B, comma, DA. This is exactly the index combination we are looking for. Sorry for crossing this line. This is equal to R, C, D, A, B. Now, we are coming to the last property we should show today. We like to show that R, A, B, C, D is equal to 0. Okay? What do we have to do? Now we have first to plug in the definition of the antisymmetrized bracket. The antisymmetrized bracket is defined as the following. It's 1 over 3 factorial, where 3 is the number of indices in this bracket, of all different combinations, where if we change one index with another, we always pick up a minus sign. It's R, A, B, C, D minus R, A, B, D, C plus R, A, C, D, B minus R, A, C, B, D plus R, A, D, B, C minus R, A, D, C, B. Just checking whether I've done a mistake or not. A, B, C, D is right. One exchange. D and C is a minus. They're exchanged C with B. Pick one more minus. It's plus again. Here exchange C, B and D. One more minus. Perfect. Plus. I exchanged D with D. Pick a minus. Again a plus. Again. Perfect. Good. What I need now is both rules from here and here together. That means I know that this is antisymmetric if I exchange in the first 2 indices, and I know if I exchange pairs of indices in this fashion, it's symmetric. In this sense, I also can exchange the last pair of indices, get a minus, exchange this pairs of indices in this way, exchange here C with D, pick up a minus, do it again in this direction, and pick up a minus at all. So let's see whether there are things like that. And it is. R, A, B, C, D goes with, in this fashion, I think it's this one. This one, I'm sorry. Last guess, I guess everything, but now I'm quite sure. This one, it's very easy because I just exchange D and C and pick up a minus again. I'm sorry. I'm running out of concentration. It's R, A, B, C, D. This both, guys. R, A, C, D, B, yeah. Now I have the I for it. It's again R, A, C, D, B. And these guys do the same trick. A, D, B, C, A, D, C, B. Perfect. As you see, playing with indices is nice, it is funny, and you get tired. So if you want to get to sleep, do that. Okay, just kidding. Okay, we now plug in the result from the second question. What was that R, A, B, C, D was a half, but I get it in each term. So it's 1 over 6 of G, A, D, B, C minus G, B, D, A, C minus G, A, C, B, D plus G, B, C, A, D. That was the first one. The second one, R, A, C, D, B. Okay, I know I have G minus G plus G. And I distribute the indices in the right fashion. A stays A. That means A, comma, A, and C takes the role of B. So C, and C. D takes the role of C. So D, and B takes the role of D. So B, As you see, normally it's enough to do it for 3 indices, but if you do it for all 4, you really can check whether you've done a mistake or not. And it's really, really, really important to check after every step that the indices are right. Otherwise, you get nice results which are wrong. Okay, ADCB, we have to see, okay, I write down the index game again, minus G, comma, minus G, comma, plus G, comma. A stays A, we already had that. A. D goes to B. And this guy, D. C goes to C, that's easy. C, and B goes to D. B goes to D, I've done a mistake. B goes to D. No, I do not have done a mistake, I just write D again. D goes to B, D goes to B, and here again D goes to B. So close the bracket and check how these terms cancel. I firstly see that I have done a mistake over here, because I see the terms do not cancel each other, and if you follow me and see that I'm not the best calculator, you see that I have an RADBC, have I made to RADB. BC. I warned you a second ago and I do the same mistakes. Yeah, you have to be concentrated. Okay, then I have to distribute the indices again. Okay, it's G. Okay, A stays A. We had this already. A. B goes to D. 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 B goes. C goes to B. 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 And D goes to C. 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 And C. Well done. So, check a second time. GAC DB, and GAC BD. We know that it's because of the Schwarz rule, it's also GDB. So these two terms cancel. Next term. My handwriting was very bad. DC. AB, where is it? It's DC AB, it's over here. CD exchange, but it's okay since the metric is symmetric. And we can do all the steps again, and we see it's 0. Altogether, what did we learn? We learned that if we exchange the first and the second slot in the RBCD, we pick up a minus sign. If we exchange the third and the fourth slot, we also got a minus sign. If we exchange pairs, that means AB with DD, what we have done here, we still have a plus sign. And the last thing what we learned is that RA of the antisymmetric part of BZD is 0. Therefore, the tutorial is finished, and we see us the next time.